Okay. It says the surface area of a cube is 6 times the quantity of a divided by 4 squared, where a is a positive constant. Which of the following gives the perimeter of one face of the cube? So first, everybody knows that a cube is like a dice, right? Dice that you play on the craps table, rolling them around. There are 6 sides of it. Okay, so if we're considering how you find the surface area of a cube, and we're going to work backwards from there. So to find the surface area, we would find the area of one side, and then we would multiply that by 6, right? And that would give us the surface area of the cube because it has 6 equal sides. So we're given this equation, 6 times a divided by 4 squared, right? And this is equivalent to the surface area. Well, if we work backwards, okay, and we were to just say divide this by 6, okay, what that does is that gives us the area of one side. So the area of one side is equivalent to a divided by 4 squared, right? So how do we find the area of a square? Well, we take the height times the width, or the length times the width, however you want to look at it. We have our square here. This would be a times 4, or a divided by 4. Those multiplied against each other would give you a divided by 4 squared. Okay, so that would be one side of it. But we're looking for the perimeter. So the perimeter is taking the length of each side and adding them together. Or in this case, since we're working with a square and all sides are the same length, it's taking this and then multiplying it by 4. So when you take 4 times the quantity of a divided by 4, because that's one of our side lengths, you can see that you get 4a over 4, which would simplify down to being just a. Because you would multiply by a, then divide by 4, or 4 multiplied by a, then divide by 4. Cancels itself out to make itself just a. So not a terribly difficult question. It's just makes you think, right? How is that looking on the video? That looking pretty good? Just makes you think as you're going through. So before we get too far into the slides, a couple properties that we talked about last week was the one-to-one property of exponents and the one-to-one property of logarithmic functions. Those are both going to come into play today, as well as our inverse functions or inverse properties of logarithms. So one-to-one property of exponents. So one-to-one of exponents. That says that if we have the same base and one of our bases is raised to an exponent that has a variable in it. So say if I have 6 to the x is equivalent to 6 to the 6th, the one-to-one property of exponents states that x must equal 6, right? Because that's the only way to make this statement true, is that x would equal 6. Okay, remember that also allows you to exponentiate, which is if we're given something, we'll say the common log of 15 is equal to 15x is equal to 6, we'll say, just for giggles. It allows you to exponentiate and add a base. So we could put both of these with 10 as the base and what we had as the exponents. So log of 15x is equal to 6. We take that 10 to the power of the logarithm of 15x. This is where an inverse property would kick in, where we would be left with 15x is equal to 10 to the 6th. We'd be able to find out what 10 to the 6th is, divide by 15, and find x. Right? So one-to-one property of exponents. Okay, it allows you to remove the base or add the base so that your inverse properties will apply. Okay, especially your inverse properties of logarithms. Okay, so that's one of the properties that we covered last week. The next one is the one-to-one property of logarithms, which states that if we have, say, the common log, or I won't even use common log, say log base 7 of 10x is equal to log base 7 of 5. Okay, you can see we have the same base for both of our logarithms. They're both log base 7. So the one-to-one property allows you to remove those logarithms. So we could set it up as 10x is equal to 5. We'd be able to divide by 10 and show that x is 1/2. So it allows you to remove the logarithms. Another thing that you can do with the one-to-one property of exponents is you can take logarithms. Okay, so let's say we have e to the 3x is equal to 15. Okay, using the one-to-one property of logarithms, I can add or take the natural log of both sides of these, and as long as I do it on both sides, my inverse property will kick in, and then I'm left with a suitable answer. So if I take the natural log in this case of both sides, okay, by doing that, you can see that the natural log of e to the 3x, okay, I use natural log because I know it has base e. This kicks in an inverse property, which states that the natural log base e to the 3x is going to be equal to 3x. So once I apply that property, I'm left with 3x is equal to the natural log of 15. I can divide by 3, and I would get my answer for x. Okay, so one-to-one property of exponents, one-to-one property of logarithms. Talked a little bit about them last week, but they're definitely going to come into play this week. Okay, other things that you'll need to know: your product property of logarithms, your power property of logarithms, as well as some of those will come into play on the harder problems. I won't necessarily say harder because it's not really arithmetically harder. It's more the amount of work to solve, we'll say. So starting off with problems from example 4. So here's one. It says we're going to solve 3 to the power of x is equal to 7. And we want to solve for x. So here, we could try to get it into a situation where our exponent, our one-to-one property of exponents works, and we could manipulate the base 3 or the base 7 so that they would be equal, right? But in this case, we're stopped right there. We can't use the one-to-one property of exponents because there's not a way that I can manipulate 7 to put it into a base of 3, right? 7's a prime number. So the only thing that multiplies into it is 1 and 7. So it makes it very difficult that way. If it was 9, right, we could put in 3 squared for 9. Then the one-to-one property of exponents was kicked in, show that x is equal to 2. I mean, you could, if you wanted to use a calculator and spend about an hour, you could try to figure out what power you could raise 3 to equal 7, which is basically solving it. Get just guessing and check. Be like 1.3, something like that. But there's a much easier way to solve it, or a much more methodical way to solve it using our properties. Okay, so this one I'm going to use the one-to-one property of logarithms, and I'm going to add logarithms to it. So 3 to the x is equal to 7. If I use the one-to-one property of logarithms to add the natural log or the common log, I always want to use or add those things that are beneficial to me. Okay, so in this case, I'm going to use natural log. It's beneficial to me because I can use a calculator. So if I take the natural log of both sides, sets it up to the natural log of 3 to the x is equal to the natural log of 7. Then I use my product or my power property of logarithms to put this x out front and multiply it by the natural log of 3. That's going to be equal to the natural log of 7. Then I can divide both sides by the natural log of 3. And I get that x is equal to the natural log of 7 divided by the natural log of 3. And then I would plug that into my calculator, which I can do. I'll get the beta calendar up, or the meta calendar. Oh wait, calculator. Today is going to be a little rough, I have a feeling. Share my screen once again. So if I take the natural log of 7 divided by the natural log of 3, oh, come on. There we go. You can see I get 1.7712. So rounded to the nearest hundredth, that would be x is approximately 1.77. Okay, other ways that you can look at doing this problem. Okay, and you really end up doing it the same way. We got our answer is 1.77. So some things that we could do at this stage, we could actually flip this into a logarithm where it would state that log base 3 of 7 is equal to x. Okay, and then if you remember, we can use the change of base formula to be able to input this into the calculator. The change of base formula is going to state that it's a log of 7, or the natural log of 7, divided by the common log. So I did common log on this one. Those are both going to be equal to x, which once again is going to be equal to about 1.7. Okay, so you got multiple ways to think about this. It's just a matter of which one fits your bill the best. Okay. So you can see, breaking it down, the inverse property at this point is probably the most important, because that's what gives you the 2x plus 1. Then you just isolate your variable. As you go on down, we're left with x is equal to the natural log of 8 minus 1 divided by 2. If I plug that into my calculator, so the clear that, natural log of 8 minus 1, this is going to hurt me, divided by 2. You can see I'm left with 0.539. So rounded to the nearest hundredth, x is approximately 0.54 away. So you can see the one-to-one property of logarithms. By being able to take the log of both sides, it allows me to manipulate my equation so that my inverse property kicks in. Okay, and I use natural log because I have the base of e. So we took the natural log of each side because we have the base of e. There's our inverse property, which just reduces it to 2x plus 1. It's equal to the natural log of 8. Subtract 1 on both sides. We divide by 2 on both sides. And then we use a calculator to solve it. So x is approximately 0.54. Here, another one. We're going to take, so we have solve 4x is equal to 9. This way, I'm going to take the common log of both sides, plug that into my calculator. So once I do that, I take the common log of both sides. I have the common log of 4 to the x is equal to the common log of 9. Power property brings my exponent out front. Divide by the common log of 4 on both sides to isolate my variable. So x is equal to the common log of 9 divided by the common log of 4. Plug that into my calculator. And I get about 1.58 as my answer. So you can see those first couple ones, they're pretty simple, not too much work involved. Remember, we can always switch this back into a logarithm and use the change of base formula to solve it. You end up doing the same thing at the end of the day. So either way you solve it, comes out with the same answer. All right. So here are probably your most labor-intensive problems. And what I mean by labor-intensive is it takes a lot of steps to solve them. Okay, first, we always want to analyze, okay, if we could get the one-to-one property of exponents to work. Here we have a base of 3 and a base of 2. There's really nothing I can put in for 3 that has a base of 2, right? Because 1 is going to be an irrational number, so it's almost impossible for me because that's going to have like 100 decimal places on top of it. So it doesn't really make sense. So we're given 3 to the power of 6x minus 3 is equal to 2 to the power of 4 minus 4x. All right. Here's where the labor-intensive stuff comes in. Okay, remember how we were expanding and condensing logarithms? This turns into that same type of problem. And I have to do this because I'm not able to substitute a base to make them the same. Okay, so using the one-to-one property of exponents, I'm going to use natural log. So the natural log of 3 to the 6x minus 3 is equal to the natural log of 2 to the 4 to the power of 4 minus 4x. Okay, now I'm going to use the power property, bringing my exponents out front. 6x minus 3, natural log of 3 is equal to 4 minus 4x times the natural log of 2. Okay, at this point, I'm still not in a good spot. Okay, what I have to do is I have to distribute these natural logs into my parentheses. What that does is it splits up this parenthesis, right? So once I do that, 6x times the natural log of 3 is 6x times the natural log of 3 minus 3 times the natural log of 3. Okay, now I'm going to distribute, do the same thing on the other side. 4 times the natural log of 2 minus 4x times the natural log of 2. All that did was it just expanded it even further. Okay, now at this point, okay, I have all individual logarithms. I have 6x natural log of 3, 3 natural log of 3, 4 natural log of 2, 4x natural log of 2. What I'm going to do is I want to isolate my variables on one side. Okay, so I'm going to take this minus 4x natural log of 2, I'm going to bring it to this side. I'm going to take this 3 natural log of 3, and I'm going to bring it to this side. Okay, since it's minus, if I add 3 natural log of 3, because that's just a number, and it's minus on this side, so I'm going to add 4x natural log of 2. When I'm done, so I'm going to be 6x natural log of 3 plus, because I got to do it on both sides, 4x natural log of 2 is equal to 4 natural log of 2 plus 3 natural log of 3. Okay, because those cancel out. And I added them on both sides. So now I've got my variables isolated. What I can do is, since these are added, right, and they're just numbers, it's 6x times the natural log of 3 and 4x times the natural log of 2, I can factor out that greatest common factor of x, because x is multiplied in both cases. So when I do that, I'm left with x times 6 natural log of 3 plus 4 natural log of 2 is equal to 4 natural log of 2 plus 3 natural log of 3. Okay, and then to solve it, just like any other one, isolating the variable, since it's multiplied, if I divide by this entire quantity, okay, I can actually put those together. And you can actually plug that into a calculator. To make it a little bit easier to plug it into the calculator, I'm going to rework it just a little bit. Okay, and what I'm going to do to rework it is I'm going to reverse the power property. Okay, and when I reverse the power property, I'm going to be left with x times the quantity, the natural log of 3 to the 6th power plus the natural log of 2 to the 4th power is equal to the natural log of 2 to the 4th power. Hopefully I wrote all that stuff down. Plus the natural log of 3 to the 3rd power. And all I'm doing is just trying to get it into a format that's easier to plug into my calculator. So basically I expanded it. I know what I have to do to solve it. I'm just trying to get it into more consistent. I have a plus between both of these. Okay, I can reverse the product property. So once I do that, it's x times the natural log of 3 to the 6th times 2 to the 4th is equal to the natural log of 2 to the 4th times 3 to the 3rd. Okay, 2 to the 4th power is 16. 3 to the 6th power is a big number. 3 to the 6th is 729. 2 to the 4th is 16, like I said. So 2 to the 4th is 16 times 27, because 3 to the 3rd. There's still a natural log up front of both of those. 729 times 16. X times the natural log of 11,664. 16 times 27 is 432. Okay, now if I just divide by this natural log, I get x is equal to the natural log of 432 divided by the natural log of 11,664. Which is approximately x is equal to 0.65. Approximately, because I rounded. Like I said, everything from this point, I knew I had to divide by this whole quantity. All of this work is just trying to get it into something that's easier to plug into my calculator. Okay, I could, in theory, take this entire thing, or take this entire thing divided by this entire thing and get it. All of this is just to put it into one solid number. Because I knew to isolate my variable, I had to divide at that point. All right, let's watch the book's explanation. So we have the original equation. They take the natural log of both sides just like I did. Okay, and then we use the power property to move the exponents out front. Once we do that, we distribute. Okay, and what that's doing is expanding this out. All we're doing is expanding it. Once we have it distributed, we want to isolate our variables onto one side of our equation. So they're going to bring this 4x natural log of 2 is 3 natural log of 3. They isolate them to one side. So you can see this term is now here. This term is now here. What that does is it gives you a greatest common factor of the variable. So you're allowed to factor that out right there. At this point, like I said, we could plug this entire thing into a calculator, but you got to use a lot of parentheses, right? It would parentheses 6 times the natural log of 3, parenthesis plus 4 natural log of 2. You can see it just turns into a little bit of nightmare. So they go back and we start combining them back together. So we use the power property, okay? Because those 6, that 6 and the 4 are our exponents out front. So we reverse the power property to put them back where they actually belong, as exponents. Then they do the product property to condense them down even further. Okay, 2 to the 4th is 16. 16 times 27 is where they get 432. 3 to the 6th is 729. Okay, and 729 times 16 gives you 11,664. And then 16 times 27 is 432. And then they divide to get their final answer. Okay, so you can see those problems are your most labor intensive. They have a lot of steps. Okay, but they're logical steps, right? We blow it all apart. We isolate the variable on one side, we factor it out, and then we're going to be able to divide. Okay, and as a little tip, if you see an x plus 2 and a 2 minus x, see how there's binomial terms in the exponents, and we don't have a base that we can get to the same base. Like 4 and 3 here, there's nothing I can do to get that to be a whole number raised to an exponent, right? If this 3 was a 16, that would be so easy, because we'd be able to put 4 squared, use our power of a power, then use the 1-1 property of exponents. We'd be left with x plus 2, 4 minus 2x. And then we'd be able to solve that pretty simply. But because 4 and 3, we can't get them to the same base, we have to blow it all apart, rework it, put it back together. And I'll show you how to do this one as well. All right. Oh. Okay, so we have 4 to the power of x plus 2 is equal to 3 to the power of 2 minus x. And it doesn't matter on this one if you use common log or natural log, either one works. So I'm going to use the common log and apply it to both sides. X plus 2 common log of 3, 2 minus x. Then power property to bring it out front. So x plus 2 times the common log of 4. And then 2 minus x times the common log of 3. Okay, now I can blow it apart even farther by distributing. So I'm left with x times the common log of 4 plus 2 times the common log of 4, because I distribute that common log of 4 in. And that's going to be equal to 2 common log of 3 minus x common log of 3. Okay, isolate your variables on one side. So I want to work with positives, so I'm bringing this part here. I'm going to take this part here. So if I subtract 2 common log of 4 on one side and add x common log of 3, I'm going to do that on both sides. I get x common log of 4 plus x common log of 3 is equal to 2 times the common log of 3 minus 2 common log of 4. Okay, so I've got it to this point where I've got my variables on one side. Now, since x is multiplied in both terms, I can factor out the greatest common factor, which is x. So x times the common log of 4 plus common log of 3 is equal to 2 common log of 3 minus 2 common log of 4. Okay, now I'm going to start to work to, I know exactly what I need to do, right? To finish isolating this variable, I need to end up dividing by this whole term. But if I put it back together, so on this side to put it back together, it's just a product property because it's 4 common log of 4 plus common log of 3. They have the same base. So that turns into the common log of 12 because 4 times 3 is 12. So that's x times the common log of 12. This one is a little bit harder to put back together. So the first step would be to reverse the power property. So that's log base 3 to the second, log 4 to the second. Okay, so at this point, I have the log of 9 minus the log of 16. Okay, and you can see I'm just reversing properties. Now this states that it's the quotient property. So common log of 9 minus common log of 16 is really the common log of 9 divided by 16. Okay, and if I plug, and then if I divide by my whole quantity here, so I'll get you that as my final answer. Let me create a little room. Take away where we started. So from this section, going up to here, to solve it, I need to divide by the common log of 12 on both sides. So x at the end of the day is equal to the common log of 9 divided by 16 over the common log of 12. So you can see it's a lot of work, but it's simple work. It's just reversing properties to blow it all apart and put it back together. Then at this point, we can look and use our calculator. So clear it all out. So the common log, 9 divided by 16 in my parentheses, divided by the common log of 12 in my parentheses, gives me a negative 0.23 rounded to the hundredths. So my answer should be D here. Okay, and you can expect that type of work when you have two bases where you can't manipulate them to get them into the same, and you have a binomial in the exponents. Okay, it's a lot of work to get it there. All right. Here we have, this one's not terribly difficult, but it's still difficult. Okay, in this one, you can see it fits the quadratic format. And what I mean by that is you can see that e to the 2x minus e to the x is minus 2, okay, where we have a constant. The quadratic, if you remember, would just be like ax squared plus bx plus c, right? The key is when it fits the quadratic, this exponent here will be double whatever this exponent is. So if this was e to the 8x, this would have to be e to the 4x. Okay, our quadratic term has to be double. Okay, rather than just one. Okay, but we have the base of e. So what we can do is we're actually going to assign e to the x as a variable. So we're given e to the 2x minus e to the x minus 2 is equal to 0. And I'm going to use the variable u, but I'm going to say that u is equal to e to the x. Okay, u is equal to e to the x. So and now I'm going to plug in u. So this would be u squared minus u, because u is equal to e to the x, minus 2 is equal to 0. Okay, and why I do that is because this is much easier to factor. Okay, it fits the form of the quadratic. Okay, whereas this e to the x or e to the 2x is a little bit intimidating to factor. So I'm just substituting in to make it more visually pleasing. Okay, so now I factor just like any other quadratic. I'm looking for two terms that'll multiply to equal a -2 that'll add up to equal a -1. Well, 2 and -1. 2 times -1 equals a -2. 2 plus -1 adds up or to a -1. So -2 and 1, sorry. So this gets factored down into u minus 2, u plus 1. Yes. Because if I were to FOIL these back out, u times u is u squared, u times 1 is u, -2 times u is -2u, -2 times 1 is -2. Okay, now they're all set equal to 0. Okay, zero product property states that one or both of these have to be equal to 0. So u minus 2 set equal to 0, u plus 1 set equal to 0, and then solve it. So this first one turns into u is equal to a +2. So I'm going to add 2 on both sides. This bottom one is equal to u is equal to a -1. And then I plug e to the x back in for u. So this top one, e to the x is equal to 2. This bottom one, e to the x is equal to a -1. Okay, at this point, you should be able to identify that one of these cannot happen. Okay, the one that cannot happen is this e to the x is equal to a -1. Right? If we remember the graph of the exponential functions, e to the x is positive. So the more variables I plug in, I'm never going to touch -1. I have an asymptote on the x-axis. So this cannot happen. Okay, for any of them where it can happen, this e to the x is equal to 2, we actually have to solve it. Okay, but the way we solve it is pretty simple. So e to the x is equal to 2. You could plug it into Desmos and actually find out what exponent it would be. Or you can take the common log or the natural log of both sides using the 1-1 property of that. Inverse, so x is equal to the natural log of 2. Because your inverse property kicks in, the natural log of 2, in this case, so x is equal to 0.69 approximately. So, and this was because it fit the form of the quadratic. Okay, remember, to fit the form of the quadratic, this first exponent needs to be double whatever this second exponent is. Okay, so like if this was e to the 6x, the middle term would have to be e to the 3x. Okay, that way we can always break it down just like that. It gives you that quadratic where you're going to have u squared minus u or plus u, and then you can factor it. So there's our original equation. We're saying that u is going to equal e to the x. Okay, and all that does is gets it into a format that's easier for us to factor. Okay, so once we factor it, we're left with u minus 2, u plus 1. So u has to either equal 2 because they subtracted, or they added 2 on both sides, and u equals negative 1. Once again, once you replace u, you can see that this right here, e to the x, is equal to a negative 1. That can't happen. Okay, it can't happen because this is a positive. Now, if it was a negative, yeah, it definitely could happen. Like a negative e to the x is equal to a negative 1. Then yeah, 100%. The signs have to match. Okay, in this case, it doesn't happen. So they actually try to solve it, but you can see you can't have a negative right there. Only solution is x equals natural log of 2 because the natural log of negative 1 is extraneous, right? There's no real solution there. Then they want you to plug it all back in. Let's check it out. E to the natural log of 2, that's 2 squared minus 2 minus 2. Inverse property on both of those. That's how they get those. And you can see the power property of logarithms still in effect. 2 times natural log of 2, that 2 is your exponent. Da, 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 da. All right, one more. So e to the 2x plus e to the x minus 12, does it fit the form of the quadratic? Yes, it does. Could there be times where it won't? Yeah, yes, there can, right? But we can manipulate them to get them to fit the form of the quadratic. So e to the 2x plus e to the x minus 12, I'm saying u is equal to e to the x. Okay, and it won't always be that case. Okay, like if this one, just for giggles, if this was e to the 6x and this was e to the 3x minus 12, it still fits the quadratic because this exponent is double what this exponent is. Just in this case, u would be equal to e to the 3x. And then I'd still get u squared plus u minus 12. Okay? So u is equal to whatever your middle term is. Okay? Or whatever e to the variable. There's a coefficient. We have to leave the coefficient. Leave it alone. Because we're just plugging in u squared. So since u is equal to e to the x, e to the 2x is u squared. E to the x would just be plus u minus 12. Okay, and then I factor, looking for two terms that multiply to equal a negative 12 that add up to equal positive 1. Terms that I think of are u plus 4, u minus 3. Okay, and this is all set equal to 0. Now zero product property, I solve it. U would be equal to a negative 4 for this binomial. U is equal to a positive 3 for this binomial. Because once I solve it, set them equal to 0 and solve. Plug e to the x back in. E to the x is equal to a negative 4. That doesn't work. E to the x on this side is equal to 3. If I take the natural log of both sides, my inverse property kicks in where x is equal to the natural log of 3. Expressed as a decimal, which they have there, so the natural log of 3 is 1.0986, so about 1.1. But in this case, because either the natural log of -4 can't happen, this one isn't viable. That's making errors in factoring. All right. These will be the last types of questions that you'll have. Okay, this one, it's pretty simple. It kind of breaks itself down where we're going to factor it as well. But we are going to use the power property or the product property of logarithms to multiply it, get it into a quadratic format. And then we'll use the one-to-one property of logarithms to drop the logarithm. Then we'll isolate and get it all set equal to 0. And then we'll be able to factor to solve. Where was that good mark there just at? Is this it? All right. So we're solving log of x plus the log x minus 3 is equal to the log of 28. Yay. Where did I pocketed? Me and my greedy little fingers. This marker's no be anymore. Stay around for a little bit. All right. So I have my equation written down. Stop sharing so you can see my pretty face, even though it's covered by a mask. All right. First step. Get these into one logarithm. Product property states that these are multiplied together. So this would be log of x times x minus 3. Okay? They're multiplied is equal to the log of 28. All right, at this point, we can drop the logarithms. One-to-one property of logarithm, they have the same base. Therefore, this must be equal to this. So x times x minus 3 is equal to 28. Has to happen that way. Okay, next step, distribute this x in. So once you do that, it's x squared minus 3x is equal to 28. Bring it to this side, so we're x squared minus 3x minus 28 is equal to 0. Okay, now we can solve it by factoring. Two terms that multiply to equal a -28 that add up to equal a -3. That is x minus 7, x plus 4, all still equal to 0. Okay, zero product property states that one of these must be equal to 0 or both must be equal to 0. So if I set them at equal to 0 and solve, so x plus 7 set equal to 0, solved, I'd add 7 on both sides. I get that x is equal to 7. This one, x plus 4 set equal to 0, solve for x. Subtract 4 on both sides. I get that x is equal to -4. Okay. Now, here's the kicker. Once I have it here, okay, I have my two solutions. X is equal to 7 and x is equal to a -4. I have to plug them back in to check. Okay, I have to plug them back in to check. So the log, plugging in x is 7. Log of 7 plus the log of 7 minus 3 is equal to the log of 28. Okay, log of 7 minus 3 is just log of 4. So log of 7 plus the log of 4 is equal to the log of 28. Product property says that these two are multiplied, get them into one logarithm. Log of 28 is equal to the log of 28. So x is 7, checks out. Okay, that's a good solution. My other one, -4 Does not. Okay, that you can see it from when I first plug it in. Plug in -4 for x. Log of -4 plus log of -4 minus 3 is equal to the log of 28. Okay, this right here can't happen. Can't have a log of a negative number. This would actually break down into the log of -7. That also can't happen. Okay, those are both because you can't take the logarithm of a negative number. Just can't do it. Okay, that's from your basic properties of logarithms, which I think was in 3.2. So the original equation, the product property, you condense them back down. Then they actually distribute. They distributed beforehand, I distributed after. Either way, you get the same answer. 1-to-1 property drops the logarithm sign. They isolate 28 on one side. Now we're going to factor. So x minus 7, x plus 4. X is equal to 7 or x is equal to -4. We plug it back in because -4 cannot happen because you can't take the logarithm of a negative number. You guys want one more or you guys feel pretty good? Because this is the last question I have. I'll walk through it. No harm in walking through it. A wise man once said, if you want people to remember something, repeat it and repeat it often. All right. So our question, we have the natural log of x plus the natural log of 5 minus x, jerks, is equal to the natural log of 6. They're going to be jerks because this one's going to give me a -x² value. Okay, first step, put them back together. Power property or product property. Natural log of x times 5 minus x is equal to the natural log of 6. Then they distribute, so the natural log of 5x minus x² is equal to the natural log of 6. That's all with parentheses. 1-to-1 property of logarithms drops the log sign. So that's 5x minus x² is equal to 6. Okay, now I'm going to rework it where I have -x² plus 5x minus 6 is equal to 0. Now what I'm going to do, okay, because I have a negative out front, I'm going to factor out -1 first. So x² minus 5x plus 6. All it does is change the sign, but it gives me a positive value here. Now I can factor it. 2 terms that multiply to be a +6 that add up to be a -5x are x minus 2, x minus 3 as my binomials. Set those equal to 0. I get x is equal to 2 on one, x is equal to 3 on the other. Okay, now I plug them back in. In this case, I have these 2 solutions. Plug them back in to make sure they work. So plugging in 2 first, it would be the natural log of 2 plus the natural log of 5 minus 2 is equal to the natural log of 6. 5 minus 2 is the natural log of 3. Natural log of 2 plus there is equal to the natural log of 6. Product property allows me to multiply those. That states that this is the natural log of 6 is equal to the natural log of 6. So 2 checks out. Next one, 3 in for x gives you the natural log of 3 plus the natural log of 5 minus 3, which is 2, is equal to the natural log of 6. Natural log of 3 plus the natural log of 2 equal to 6. Product property says that these 2 are multiplied. natural log of 6 is equal to the natural log of 6. That one, they both check out. So our final answer is going to be 2 and 3. We don't have that. Nope. All righty. That's what I have for you. Okay, we're not going into example 8. It's more or less the same exact thing. So you can see on this one, they're going to rework it. Okay, they brought it all over there as one. Then they carry out the quotient property, the inverse property. Pretty simple stuff. Nothing too terribly difficult. All right, but that's your lecture for today.